Hello everyone! We are going to prove the triangle angle sum theorem, which tells us that in a Euclidean space, the sum of the measurements of the interior angles of a triangle is 180 degrees. Notice that the claim is that we are on a Euclidean space, also given to be a Euclidean geometry or the plane geometry. We need to show that for all triangles in the Euclidean space, the sum of the measurements of the interior angles of any triangle is 180 degrees. Actually, we already have proven this theorem in the previous video. You might want to view that video on your own time. Here, I'm going to show another proof for this theorem, but this proof now is by construction. Let me share to you this triangle here. So I simply cut a triangle, and using this, I'm going to show you the proof of this theorem where the measurements of the interior angles of this triangle here must be equal to 180 degrees without any sentence or use of words. How do I prove this theorem using this cutout triangle? Let me do it this way. I have here a triangle. Definitely you would know that a triangle has three sides, three vertices, and three interior angles. Again, this angle here, this angle here, and this angle here. I will show you that the sum of the measurements of all of these interior angles is 180 degrees according to the claim here by folding this into a specific figure. Let me choose a vertex for this triangle where I'm going to start folding. Let me use this vertex and I'm going to fold it on the intended process of proving this theorem. I'm going to fold this here, this vertex, as this will intersect the opposite side. Its opposite side is this here. Okay? But my folding should be in a sense that the folding made should be parallel to this opposite side. I'm not going to fold it in any way like this, like that. I'm going to make sure that my folding for this vertex to the other side be parallel to this side as well. I'm talking about doing this. I'm going to fold this here, touching the other side, but making sure that this is actually the folding made here is parallel to this side here. So I don't know, let's try. So it's like this. Okay, so assuming that my folding is correct, this folded portion here is parallel to the bottom side here. Okay, that's my first step of proving this theorem. To continue, what I need to do is to just connect the other two vertices here and here to the vertex or to the intersection of the folded vertex in this opposite side. I'm going to make sure that this vertex here be folded in such a way that when I fold this one, this portion or this side will be parallel to itself. Same as true with this side here. Let me do it like this. So I'm going to fold it, make sure it's not like that, it's not like this, but it should be parallel. Parallel here. Yeah. Parallel to this side as well. Again, like that. Here. This side here. Okay? So I'm done with this vertex here. I'm going to do the same thing on the last vertex, but then again, not like that, not like this, but parallel to this opposite side here, or to this side rather. So I'm going to make sure that, okay, just doing it like this so that it could actually be done properly. So it's like this. Okay, like that. Let me do it again. Okay, this is our original triangle where I chose one vertex and folded it this manner, where the folding is parallel to that opposite side, and I'm tried to make sure that my vertex here will touch that opposite side here. In doing so, for the remaining vertices, this and here, I folded it in a way that the folding will be parallel to this side. And it looks like that, and to the other side as well. So pardon if my figure or my triangle is not that straight, but if it's really straight when it comes to the edges, okay, it will fit everything here. Now, what is the purpose for this? Again, I would like to show the proof of this theorem using this folding process. Let me try to draw this here. So this angle here. Okay, assuming that again my triangle is perfect, like that. All right. So it's like that, like this, and this one. I made a angle covering the three connected vertices on this side. So again, I made like that, this one here as well as here. If you would like to, you could also shade it if you want. I'm shading it like this, I'm shading it like that. So this is the angle form. Notice that the angle form here is actually equal to a straight angle. Straight angle in a sense that this is here, this side here is actually your line or segment if you would like to, and this is the angle form. So if this is a straight angle, in short, this measures 180 degrees. The three angles here measures or sums up to 180 degrees. To continue with this proof, I need to return this folding into the original form of a triangle. Again, beg your pardon if it seems like it doesn't necessarily connect from one to the other because probably my cutting is not that straight. But if it's perfect, it should fill in all the way here. So again, I'm going to return this to the original triangle. Okay, so like that, return, return, return here. So this was my original triangle earlier, and we just folded in such a way that we could actually show this straight angle here. This is the proof for this theorem because once I will flip this, look at the angles formed. Notice that the angles shaded earlier were this angle here, that angle at the top, and this angle here on the other side. These are the three angles formed earlier under the folding process, which comes up or results to a straight angle. When I returned it, all of those three angles that makes a straight angle became the original vertices or the angles rather of the cutout triangle. This means that the sum of these three angles here is making a straight angle which measures exactly 180 degrees. This came from here, straight angle 180 degrees, but they were actually the interior angles of the original triangle. This is another proof for the triangle angle sum theorem, which tells us that in a Euclidean space, the sum of the measurements of the interior angles of a triangle is 180 degrees.